Welcome back. In this video, we'll be looking at definition 1.5.5 and example 1.5.11. So now that we've proven that the choices of C1 through Cn in this expression is unique, we're going to give it a name. So let B be a basis for a vector space V, and let little v be any element of big V. The coordinates of V relative to the bases B are the constants C1 through Cn, so that V is C1 V1 plus C2 V2 plus Cn Vn. All right, so we said they're unique, so we're giving them a name, we're calling them the coordinate. And then the coordinate vector of V relative to B is, and now we're going to put these coordinates in a vector. That's it. All right, so let's try an example to see what this does in real cases. So let's say I have this basis here for the Euclidean space of dimension 3. I want to find the vector, so I want to find this for this V. So that means I need to figure out how to write my given V as a linear combination of the 3 basis vector. So we need to write as C1 520 plus C2 second basis vector plus C3 third. All right, so to solve this system in terms of C1, C2, remember we put the building blocks first, and then we put the target next to it, and we're going to reduce. I've actually reduced it for us already, but because it's a basis, we already know that the coefficient matrix will reduce to the identity. And then whatever's on the right, those are going to be our coefficient. Oh, ooh, sorry about that. There we are. Whatever's on the right, those are going to be the coordinate elements and then coordinate vectors. And so we have C1 equals 2, C2 equals -3, and C3 equals 5. And so the vector is 2 minus 3, 5. All right, so that's how you find the coordinate vector of an element. Now let's try to go the other way. Let's say I give you the coordinate vector of an element and I want you to find W. How would you do it? Well, we know that W is C1 times the first vector plus C2 times the second plus C3 times the third. And then what we're given here, that is C1, C2, C3. So in fact, we would actually be able to write W right away. It's 3 times this one, minus 1 times 0, 1, 1, plus 14 times 3, 3, 2. And all you have to do is compute. You don't actually have to reduce in this case at all. So I would get 15 plus 42, so 57, and then 38, and then minus 1 plus 28, 27. Oh, wait, I don't have 28 minus 1, 27. Something off. Oh. All right, so that's W. All right, let's try to do this in more general terms. Let's say I have a random W right here. I want to find the coordinate vector. So I'm going to do the same process that I did right here, but instead of having specific vectors, I'm going to have A, B, C. All right, so I'm going to plug in 5, 2, 0, 0, 1, 1, 3, 3, 2, and A, B, C. I'm going to reduce, and I'm going to get 1, 0, 0, 0, 1, 0, 0, 0, 1 as always. And then on the right, it's going to be a bit more complicated. I'm going to get minus A plus 3B minus 3C. I'm going to get, I've done it for you, so I'm not doing this in my head. I actually did it ahead of time. So minus 4A plus 10B minus 9C and 2A minus 5B plus 5C. All right, and so we get the coordinate vector of W would be minus A plus 3B minus 3C minus 4A plus 10B minus 9C, 2A minus 5B plus 5C, because really here I'm getting that C1 is minus A plus 3B minus 3C from the first equation. I'm getting that C2 is minus 4A plus 10B minus 9C, and I'm getting that C3 is the bottom one. And so those are the coordinates. That's what I put right here. All right, so this would be one way of solving the problem. Let me show you a second. All right, so I'm going to take Q to be the coefficient matrix of that system. So really, I have my 3 vectors from the basis as my column vectors here. And let's say that WB, I don't know what that is, but let's say that it's C1, C2, C3. All right, so if I knew WB, then I could do the same reasoning as I did in B and say that W would be C1 times the first vector plus C2 times the second vector plus C3 times the third vector. Don't know if you remember this, but you could see a linear combination as a product of matrices. Let me show you. So I get 5C1 plus 0C2 plus 3C3. I get 2C1 plus C2 plus 1C2 plus 3C3, and I get 0C1 plus C2 plus 2C3. And I could write this as Q. So Q was the 3 vectors like this. And then when I multiply, I want this part to be multiplied by C1. I want the following part to be multiplied by C2. And the final one will be multiplied by C3. And that's going to be true for every single row. And so really, W is Q times the coordinate vector. And so if we actually want the coordinate vector, we could take Q inverse times W. And that Q inverse, I computed it using a computer, and I got minus 1, minus 4, 2, 3, 10, minus 5, minus 3, minus 9, 5, and A, B, C. And if you multiply it, you'll get minus A plus 3B minus 3C minus 4a plus 10b minus 9c, and that's a 2, so 2a minus 5b plus 5c. And it should match what we had here. They're the same. All right, so it seems like the problem that we had in B is more straightforward. It's easier to go from the coordinate vector back to the original vector. But what's nice is that is just multiplication by a matrix in the Euclidean case, and so we could use the inverse to get the coordinate vector.